Hey, what's up, guys? This is Chung here. So today, let's take a look at this 1397. Find all good strings. So this one is a pretty hard problem, and this is like a follow-up problem after yesterday's problem, which is number 1392. So, and this problem is another problem. Also need to use the KMP algorithm. But anyway, let's take a look at the description of this problem first. So given the string s1 and s2 of size n, the string and the string evil, return the number of good strings. And a good string has a size n, which means a good string has a size the same as s1 and s2, and it's between basically, and it's alphabetically between the s1 and s2 inclusive, right? That's why it's have a equal to s1 and equal to s2. And it does not contain the string as a substring. And since the answer can be huge number, return the modular of that 10 to the power of 9 plus 7. So what does this mean? It means that, few examples here, right? So we have a S1, S2, A, and DA, and the number of courses to actually we don't need this n, right? We can just simply get the length from this either S1 or S2 and the evil number, evil string B here. And the answer is 55. So why is that? Because from the starting point we have AA, right? So AA is one, and the next one is AB, right? And then what AC? Let's say we fix we fix A first, right? And then we AC, AD until AZ, right? Because all the other characters are lower letters, but since B including the B, right? That's why this one is gone. Okay, and then we have a B. Basically, all the letters starting from B, BX, BA to BZ, they're all evil numbers because they all contain this B, right? And then we have a C here, C, CA, and then CB, CB until to CZ. Again, this CB contains B. And finally, we have D and A because that's the end, right? Basically, we stop at DA. It has to be between AA and DA. So how many here we have here in total? So from A to AZ minus AB, we have 25, right? Same thing for CA to CZ minus CB, we also have 25 here, plus this DA1. That's why 25 plus 25 plus 1 equals to 51. That's how we get this 51 here. Okay, and some more examples here. So this one, okay, so the evil number is this. So basically, there's no such the good numbers that does not include the evil number. Okay, so how can we approach this problem, right? I mean, the main logic is pretty straightforward, but what's make this one a hard problem is how can we improve the performance so that it can pass all the test cases. If you look at the constraints here, right? So the n is within the 500 and the evil number is within 1500 number. Is within 50, 50, 50. Yeah. So for the brute force, right? What's gonna be the brute force way? So at each location, we have 26 numbers in total. Let's forget about the S1, S2, right? And then we have n characters. So which means the total combinations for the string is what is 26 to the power of n. And with n equals to 500, if we do a brute force way, it'll definitely TLE. Right, that's only for that. Like assuming we have a substring here, we have a like a strings between S1 and S2, still we have S here. We still need to check if S contains this evil here, right? That's another level of the time complexity. Okay, so but that's gonna be our basic approach. So nothing too fancy here. You know, we just try to get each of the numbers, at each of the strings between S1 and S2, and then we compare, and then we check if that number, if that string include the evils here. If it does, then we just skip that. Otherwise, we continue, right? So the basic logic is like this. We start from the index 0. We start from index 0. Let's say we have a let's say we have a b c d, a b c d, and then we have a d d a a a. How about this? Let's say we have a four letters here. So the logic is straightforward. So at each of the index here, we start at I here, right? So we're gonna have like a dp here. So the first one is the index. So the index represents the current location, current numbers, right? And then so it means that at the current location. So what's going to be the range? Let's say we are at how about I'll do this. I'll do like a F here. I'll do F. I'll do a DFAA here. I mean, ideally, right? We're thinking about, okay, if we can we just simply use between this B and F, right? Let's say if we're at this location here, let's say I is here, can we use B and F? Probably not, right? Because it depends on what are the previously strings here. Then we know what's gonna be the numbers. What's gonna be the next values we can use here. So why is that? Let's say previously we have A. Let's say for the first letter we use A. Then it means that for the current letters we can only choose the B between the B and F. Otherwise it will not satisfy the conditions, right? So because the final string should be between these two strings here, right? That's why if if the the I until the I minus one is a prefix of either of S1 or S2 here, then we have to either use the B or the F, because if we have, let's say if we have a number B here, if the first letter is B, then from the second letters here we can choose from A to Z, which means we don't need to care about the upper bound, the lower bound, or the upper bound. We can simply do A to Z because the B is between A and D, right? So let's say we have a start here, we have a start, and then we have an end, right? So if the previous string is the same as the S1, basically if the previous string is a prefix of S1, then the start has to be B. Same thing for the end point, right? If the prefix of the current string is the same as the S2, then the upper bound has to be the same as F. Otherwise, we can choose anything between A and Z. Okay, so that's the first thing we need to know, right? And in order to do that, I mean, of course, the most naive way is we just simply record current string, right? And with this current string, we can easily check if this current string is the same as the prefix of S1 or it's the prefix of S2, and then we can simply get that. And also, if we have this current string here, we can also check if this current string contains the evil number, right? If it contains the evil numbers, we can simply stop this branch because we know since the current string already contains evil number, there's no need to continue our our exploration because it's already a evil number, right? So, but the problem for passing this current string here is that first the length of the string could be up to 500, and second, if we have the strings here to check the if this current string is the same of the prefix, it's going to be another length going to be a O of n here, right? Because it has to be compared with S1 and S2 two more times. That's why it's going to be another O of n. And also to check if this current string, if this D, if I'm sorry, if not D, if this evil number is already inside this current string, that's going to be another O of n. Assuming we use the KMP algorithm, because we'll be using the KMP algorithm later on for in this problem, and it will TLE. It will definitely TLE. So that's why we cannot simply pass the raw string to each of the DP function. We have to find another way of doing it. So the way is that, so for this kind of start and end, since we already discussed about the issue here, right? So all we need to know is that if this current string is a prefix of S1, if it is, then it means that the current start has to be starting from the B here. And then a second one is that if the current string is a prefix of S2, if it is, then we have to start from F, otherwise from A to Z. So instead of passing the raw strings here, besides this index here, right, we can pass two more parameters. The first one is S1 prefix. Okay, and second one is S2 prefix. Okay, so that's going to be the three parameters. And the last one is what? Okay, so we have this S1 and S2s, right? And the last thing we need to check is that we need to know until the current location of all the prefix, right? Basically, if the current string contains the evil number, but without the current string, how can we know that, right? Since we're only like passing this index and these two parameters. That's why we need the KMP algorithm, because if you guys recall what is the how this KMP algorithm is implemented. Basically, first we'll be creating like a list. So this list is called the longest prefix as a suffix list. It means that it's telling us at each of these evil numbers position, what is the longest prefix and as the suffix. So I will briefly explain that a little bit here, but for those who wants to know the full algorithm for KMP, you can either search on YouTube. There are a bunch of other like videos talking about KMP, or you can look at my the video for 1392, I believe. I gave a pretty detailed explanation about how the KMP algorithm works. You guys are welcome to watch that one as well. So Okay, so what is a KMP, right? So the KMP is an algorithm to find a pattern inside a string. So let's say we have a mm, CDA, CDA, CDC, right? So for those who already know the KMP algorithm, you guys can skip this part and fast forward into the remaining the later uh, to the part where we start coding this problem. Okay, so the KMP is like this, a brute force way of finding the pattern in the string is let's say we have M here and we have N here, right? So the brute force way is that we start from each of the index here. We start from here and then we check starting from here, can we find a match, right? And then starting from D, if we cannot, then we start from D. If we can, we start from A, from C until we find a match. And obviously that brute force way, the time complexity is O of M times N, right? And the KMP is algorithm that can improve the uh, the time complexity to O of M plus N. So the way it's doing is that we're maintaining basically based on the patterns here, we're creating like another list that tells us this is the longest the longest prefix as a suffix at the current location. So at the beginning, so why this prefix and so why this prefix as a suffix is so important? Okay, because let's say we have CDACD, right? So at A here, A and C they're different, right? If A and C they're different, so what can we do if we know like the as you guys can see here, right? So the CD is the is a prefix as a suffix at this location. So which means here we have a 2, right? It means that from 0 to this location to these positions, we have the longest prefix as suffix is 2, which is the C and D in this case. So the way we're using is this like so whenever we find a difference, a mismatch during the string matching, we basically will look for this number, the LPS values, uh, before the current index, which is this location. And if we find and in this case it's 2 here. So 2 means that, okay, since we, since that, which means we have a suffix and we have a suffix length of 2 as a prefix. So which means that we have a C and D here, right? And the C and D is the same as this C and D, right? And also since the C and D is also the prefix, then we know, okay, so the prefix is also a C and D here. So it means that we have already matched the C and D at CD because to find the patterns we always need to start from the beginning, right? But since we have already pre-calculated this longest prefix and suffix list here, we'll skip this C and D and we can start matching from this A here, right? Because by simply looking at this strings here, it's pretty obvious, right? Because we have a C and D here, and now we can simply start comparing this A and this A here, and if they're since they're the same, we can continue our mappings from here C, D, and C. That's how we improve it because the the pointer for this S will always moving forward. It will never go back because because this LPS will help us to record what's going to be the next position we need to start. Otherwise, if we don't have this, we always need to go back to start from the beginning, right? That's where this times n coming from. But since we have a 2 here, right, we don't need to go back. We can simply have a O1 time move the cursor to where it should be, to where the next number, the next letter should is supposed to be, and then we can keep comparing uh, to with the next number. Okay. Yeah, so that's that, and the way we're building this LPS is that we are like maintaining a J and an I here because the prefix has to be smaller than the string, either prefix or suffix. That's why the minimum length of the string is 2. That's why we have J and I here. And whenever the I and J is different, we so the way this is how it works. If they're not if they don't match with each other, we put 0. So A and C they're not. If they're not matching, we move I forward. A and C they're not matching, still 0. And now we move I to here, right? And then now C and C is the same. Okay, so which value we put it here? We put J plus 1. So here is always J plus 1. Remember, J is the index. So why is J plus 1? J plus 1 means that, since J is the index and we are like recording a length here, right? That's why we need to do a J plus 1. It means that from beginning to these locations, the longest prefix and suffix is 1, which is C. And whenever we find a match, we will increase both I and J. So now we have J is here, I is here, and we continue our comparison. The D and D are the same, which means that we're gonna have like a J plus 1 here, right, which is 2. As you see, because since if the J is at this location, it means that okay, we have like a match. We already have like a prefix before J, and that's why we are trying to find uh, a longer one based on the current J, and we find a 2 here. Okay, and now J is here, I is here, right? And A and C they're different. That's why whenever they're different, we'll move this J back to the location where its value where the previously value it represents, which means that we'll move the J to the value which the which this J minus 1 LPS like represents. It means that, since the current one doesn't match, and then I, I will I will try to see if the previous one has another match for me with the current C here. Just like, so since the previously the LPS J minus 1, the value is 0, which means that we'll move this J back to the 0. And then we do another comparison. Since the I and J they are the same, then that's why we have 1 here. Okay. Yeah, so basically that's how we build this LPS here. And like I said, since we already have this LPS, we can simply just do a O of m times n time complexity to find a match. Okay. All right. So back to our problem, right? Do you guys still remember? Now we have a DP, we have a I, and we have a is S1 prefix, right? And we have a is S2 prefix. The last thing we need to do is that we need to know if the previously if the current string contained this evil, right? So with this LPS, how can we do it? remember uh, the LPS stores which of the next location, right? Where is the next the matching locations? It's I mean it's gonna be. So that's why we can simply add the force parameters like the matched, you know, matched evil, matched evil letters. So this one means that, you know, at the current state, how many matched evil strings that the current string has already done. Okay. And if we have that information, we can simply start from this we can simply use that number and to find the corresponding evil strings based on this LPS. Okay. So for example, right, let's say uh, hmm, so with this matched evil numbers, let's say for example, if this number is 5, so it means that we have matched the numbers from CD, ACD. Now we're trying to compare the C here. Okay, and so basically here we're gonna have like a start and end, right? So here we're gonna have a for loop here. So we're gonna loop through everything, right? Everything either from A to Z or from the B to E, B to F, based on this is S1 prefix or is S2 prefix. And this is gonna be our current character. And we can simply uh, try to compare if this current character is the same as the index of this p here. So keep in mind here. So we have this is like the length, right, which is one base, and here is a zero base, and we can simply compare since 5 is the c here, and if this letter c here is matching the current letter, then we know okay we find another match of the evil match here. We match the evil length, right? And then we'll simply increase this one by 1, and then we'll send it to the next DP. And if the current C is not the same as this C here, then we'll simply go back, right? We'll simply go back to the 1 here because that's going to be the 1. So 1 is J here, right? So the J so the current index, sorry, so which means that this matched evil, the number will go back to 1. So 1 means that starting from D here, can we find another match? And still, if this currency is not even the same as the D here, right? And then it will keep going back until it reach the end, reach the beginning of this of this pattern here. Basically, this is this is all in the KMP algorithm. How we can find the matching strings. Same as exactly same as how are we going to use this like LPS, you know? And basically we use it the same way when we're doing the DP here. And so why we're maintaining these things here? So it means that whenever this matched evil numbers is the same as the length of the evil here, right? So let's say the length of the evil is m. So whenever the matched evil is the same as m, then it means that okay, we have find an exact match of this evil number, and we can simply basically break that branch. That's all we need to know. That's all. That is everything we need from this matched evil. Okay, so I know this problem is a bit like a long explanation. I'll start the codings, and even for the code is a little bit messy, but okay, try to stay with me. I will make it as quick as possible. So the uh, the main part. Okay, so like I said, I'm going to define the DP part first because the DP part is pretty straightforward, and the main part is like this, and we'll call the DP is like the index, right? The index and is S1 prefix, right? And then is S2 prefix, and then the last one is the matched evil length. How about this? Okay, and we can simply return this DP. So I'll define the mod here, 10 to the power of 9 plus 7. So we simply return a DP. So at the beginning it's 0, and its prefix is true because with 0, and because for the first two letters in S1 and S2, they have to be in the range of A and D, which is the same logic as its prefix equals to true, right? And the match evil length is of course is 0. And then we'll simply just do this, do a mod 10 to do a mod. Okay, so yeah, that's the the main logic. Okay, so like I said, we're gonna have like a start and end. So what is gonna be a start? Like I said, if if the is S1 prefix is true, then the start has to start from this index, the index in this S1. And since this one is S1 is a string, and we need to loop through from the string to string, I will convert this string into an integer. That's why I'm gonna use like the ordinal in the Python, which will convert as a character into its integer value. So we use this one if is S1 prefix, right? Else ord A. So this one is what it's doing is if the current if the current string is a prefix of S1, then we have to start from 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 the letters, right, of this index. Otherwise, we can simply start from A. Same thing for the end, right? I'm going to copy it, paste here. The only difference is that is 2 index and S2 and then Z. Okay. All right. Then we have an answer here, and then we have a 0, and then we have a for loop here, right? For I in range of start and end plus 1, right? So that's that. And then in the end, we simply return the answer here. And since we have a for state here, you know, this is like a DP, right? Which means we need like memorizations. But since this code is already long enough, I'll just use like a shortcut, for in Python. Basically, I'll just set this the memory cache equals to none, which means the Python will do this memorization logic for me. Whenever they see us parameters, right, with the same the four values of the same parameters, it will just return the value it's the system stored, and it will not do a continue. It will just break. Okay. So here, like I said, right? I mean, and what we need to check here, right? So here we need to check you need to check if update. Basically, you need to update the matched eval length. You know, based on the current letters, we have a C, right? We have a current C here. Current character equals to the uh, we're gonna a CHR will convert this the numeric value into its string character format. So here we need to update this match eval length. So why is that? Because here at the beginning, if this matched eval length is the same as the length of the eval, which is the m, then we simply return 0 because we know, okay, so this is not our one of answer. This is like an eval string. It's not a good one. Okay, okay. Since we're here, I will also write down the base case for our case and for our DP. And if the index is equal to n, it means that okay, we have find a good number, right? Without this matching, without matching the eval string, right? And then we simply return 1. So that's why we need to update this match eval length. And how can we update that? Right? Based on the current the character and and this eval string. That's why we need to build we use the KMP solutions where we will be building that the longest prefix and suffix list here. Let me try to build that real quick. So I'm going to have like a longest LPS, right? And then we have at the beginning, everything is the same as it's a 0. And then like I said, we're gonna have like a 0, right? J equals 0, the 2-pointer, and I is the same, is in the range of 1 plus m. So we start from 1 because the for the prefix and suffix, it has to be smaller than the original string. That's why we have to start from 1, which means we have CD A, CD, C. Because the string itself, remember this LPS, it represents by this from 0 to this index, the the substring from 0 to this index, what is the longest prefix and suffix? And for single letters, it will always be 0. Okay. So this is how we do it. Basically, we do a while j is greater than 0, and if the eval, right, if the eval I is the same, not the same as the eval j, we revert back. We revert back the j to the value of the LPS represents. Okay, so now when we are at this when we are at this location, either the eval I and is equal to the eval j, or the j is equal to 0, which means that okay, we have fall back to the beginning of the of this eval string here. So that's why we need to do another check here. Eval I is equal to eval j, and then we do a LPS I is equal to the j plus 1. Okay, because here we have a C and D, so 0, 0. And then since C and C is the same, right? That's why we do here, right? We do a J plus 1. Uh, yeah, I think here we also need to do a J plus 1 here, because whenever we find a match, we need to increase both I and J, right? And here we have a 2, and we have like 1 here. That's how we build these things here. Then this is the logic here. Okay, so Okay, with this LPS here, now we can update the matched eval length here. Since it's within the for loop here, I'm going to have like a temp length. Okay, temp eval length equals to this. Okay, and after updating that, I would just do this. I'll do an answer plus dp of index plus one. Okay, and here, right? So here we also need to update this is S1 prefix. And how can we update? How can we do that? Based on the current C here, we can simply update that. If previously this one is true and the current C is the same, uh, uh, if this I, right, or if this I is the same as the if the current C is the same as the S1 index, basically, if let's say we have a ABC, A, B, C, D, E, F, and we're at like this A and B. This is our current index. Since at this state here, the is S1 prefix is true, right? Because A and B are matching with this A and B. Now we're looping through this current C here, right? We're gonna starting from C, D, E, F, G, blah blah blah, right? And if this one is a C, then it means that the next state, this S1 prefix is also true. If this one is D, then it means that it's false, right? That's how we update these things here. Basically, is S1 prefix, right? And what? And the current C. Well, actually, we can either use like a string to do the comparison, or we can simply use the integer to do the comparison. Either way is fine. So I'll just do integer if the current I is the same as start. Okay. And same thing for the other flag here is S2 prefix and I is equal to the end. Okay. And then we have a temp length, right? Now the problem is that how can we update that? How can we update this like the temp length, right? It's exactly the same way. How are we using this LPS to find a matching numbers? Uh, so basically, while TMP TM is greater than 0, and the current C is not the same as the eval of these things, right? And then we do a TMP equals to LPS minus 1, okay? And then here, if the C is equal to the eval here, and then we update this one to do we do a plus 1 of that. Yeah, I think that should be all for this problem. Let me try to run this thing real quick, and I'll explain a little bit more here. Yeah. So 13 is S2 pre. Okay. Yeah, current C here, and run code. What out of range? Let's see. Hmm. Okay, let's see. Yeah, I think I know where what is the problem here. So here I should use m instead of n here because this the matched length is bounded with the length of evil, not the n. That's why we need to use m here. Run the code here. Cool. Submit. Okay, cool. So it's accepted. I know you guys are, I think you guys are still kind of confusing. Maybe especially for this part, right? I I agree. This is the most confusing part, even for me. So other than that, it's just I think it's regular DFS, the DP, top-down DP, right? Plus a little bit handling for this kind of the starting point and ending point, right? Why this thing works, right? I mean, maybe I'll try to write a little bit for the helper functions, right? I mean, let's say if we continue to check the patterns, right? The pattern for the current S, okay? That's basically the other half of the KMP after building this LPS, right? And now let's say given this LPS and we have a S, we want to know and if mm, if there's a pattern, right? If there's a pattern exists in that S, and how can we do it? So we have a j equal to 0, and then we have a for I in range of n. Okay. Same thing for while j. This j, this is the pointer that telling us what is the next letter we should match. At the beginning is 0 in evil. Okay, in evil, right? So while j is equal to greater than 0 and the si is not the same as evil j. Okay, then we do what? We do a j equals to LPS j minus 1. Okay, and then if the si is same as the evil j, right? And then we do what? We do a j plus 1. And if the j is equal to the n, then we return true. Otherwise, we return false. Okay, so basically that's the other half of the KMP algorithm. This is how we use this as LPS. And as you guys can see, at each of the at each of the character here, we use this J to tell us, basically this is J help us track how many letters we have matched so far, right? With this evil. And if it's still matching, right, and then we increase this J by 1. And if it does not match with the current like marker here, we'll uh will revert back. We'll revert back to it where it should be. And then we start from there again. And this J is exactly the same as this matched evil length here, right? And this matched evil length is doing the exactly the same thing as this J here, which is telling us what is the next letter we should match in the evil. See? And that's why basically, this for loop is representing the DP here. Uh, yeah, it's like this DP. And here, this current C here, the current C is this SI here. and the j is the same as this matched eval length. And as you guys can see here, we have exactly the same code as in what we have here, right? And here we're doing the same thing because here it's telling us, okay, we have matched this many letters so far, and let's see if we can continue our matching here. If we cannot, then we'll go back to the place where it should be, right? By doing this while loop and if, so that the next DP can use this value and moving forward, so and it won't look back. Okay, I think I have explained everything, right? So what's next? Oh yeah, so the time and space complexity, right? So for the time complexity, right? So the time complexity is the actually it's the for the top-down DP, right? I mean, it's the so for this part that's pretty easy, right? This is O of M, right? And we can just ignore this part for now. And the main time complexity is right here, right? The DP. So what's gonna be the DP here? We have four state, which means that in total, so the total state should be this one, the prime state 1 times 2 times 3 times 4, which is so the first one, the index, right? The index is it's bounded with n, and the second one is matched eval length, which is the m, and what? And we have like two flags here. So the flag is either true or false, right? So this one is like how many? Two, right? Either true or false. And a second one here is the last one is also a true false flag. That's why we have this many of state. Okay, so that's the state number of states, and of each state we have a for loop here. So the for loop is like it's the at most 26, right? That's why we're gonna have like a 26 here. Okay, and here, and so part of the KMP algorithm. So for this part to find the correct location, it's O1. It's O1 time complexity. I think this can be approved. Can be proved. I'm not going to. I'll just assume it's O1. So that's why the total time complexity for this is n times m times 2 times 2 times 26. Okay, that's the time complexity. And the space complexity, of course, without this 26, it's going to be a n times m times 2 times 2, which is the total state of this problem. Cool. Yeah, I think that's it for this problem. Yeah. Uh, Regardless if you understand this problem or if you like my explanation or not, I appreciate you guys for watching such a long video, and I'll just stop here and stay tuned, guys. I'll be seeing you guys soon. Bye bye.